I'm gonna read.
I remembered. Okay, so we'll talk about some active devices. Again, still analog. We won't do digital till week after next. So we're going to talk about transistors, basically, two types, bipolar and field effect. So after they discovered the semiconductor diode with a P and an N type material, somebody discovered that if you added a third piece, you could create a basically a diode where you could control the current flow. So there was two ways to do it. You could have an NPN or a PNP. And they just kind of work opposite to one another as far as the current flow. So that was the early bipolar junction transistor, which is just those three materials joined together. It turned out that in Bell Labs guys discovered the field effect transistor before this, but they couldn't make it work because of some surface things or something like that. So it was quite a while before there was an actual working field effect transistor.
I was gonna say, I used them.
Huh?
I used field effect transistors before.
Oh, I'm sure you did. My first transistor, though, was a bipolar, a CK722 by Raytheon. I saved up my money in high school. It was like $4 or $5. I still have it somewhere.
Oh,
So the other one besides bipolar or field effect, the basic difference is the bipolar junction transistor, they just call them bipolars, is a current control device. In other words, you apply current to the base to control current between the collector and emitter. Whereas a field effect transistor works just like the old vacuum tube. You apply a voltage which creates an electric field, and it controls the current between, and we now call these source and drain, because they recognize that electrons are actually moving opposite to current flow. So what would be the emitter equivalent on a field effect transistor becomes the source, and that's the source for the electrons. And the drain is where you pull the electrons out or inject holes, depending on how you want to look at it. This is a typical cross-section of the way a bipolar junction transistor is manufactured. So we have some N-type material, and we embed in it a small layer of P-type, and then in that, a little N-type. You notice it's not symmetrical at all. The collector is usually much, much larger than the base or the emitter. And the way it works, without really going into all the physics, which you don't really need to know at this point, is that when I apply a current, I'm actually injecting holes into the base material, and that flows from base to emitter, that it causes current flow between the collector and emitter that is some multiple of that base emitter current, which is, they represent it as a thing called HFE, or the gain. So that's how it becomes a controlled element. It takes a very small base emitter current to control a large collector to emitter current. This is a typical circuit of how you would bias a bipolar transistor. So we've got a voltage source here applying a bias voltage or current into the base, and these are called the base, the emitter, and the collector. So this base emitter current, which is plotted over here as the red line. So when the base current is 0, which would represent this, it's at what we call cutoff. So there's no current flow between collector and emitter. And depending on this load resistor, which determines the slope of the load line, where these two cross is the voltage that you would see across the device. Likewise, if we increase this current base emitter up to the saturation point, which would be this one, at that point, the transistor is at its lowest resistance, maximum current flow, limited by this resistor. So that's what we call the saturation point. So we normally would operate to use this as an amplifier. We would set this bias current somewhere in between saturation and cutoff and be able to operate in that range. If we wanted to use it as a switch, then we either apply 0 volts or 0 current, or whatever the saturation current is. So the device is either going to be on or off. It acts as a voltage or a current controlled switch. There I just plotted from current or cutoff to saturation versus base current. And they're on 2 different scales, so it's not as easy to see. And then what the voltage across the collector looks like as the base current goes up. So we're going to go from cutoff to saturation. Okay, so next we're going to talk about field effect, which are similar but different. Like I said, it's basically like a vacuum tube, and it's a voltage control device to control the current flow. We have lots of different types, even more than are shown here. The first ones were JFETs, or junction field effect transistors. And it was somewhat similar to a junction transistor, but it works with a electrostatic field controlling the current flow between the source and drain. And the next group are called MOSFETs, or metallic oxide semiconductor field effect transistors. And the symbol you see is different. And there's 2 types of those: depletion mode and enhancement mode, which you don't really need to know.
One is on all the time until you cut it off. The other one's
Right, they work just the opposite. Right. One is like the triode, where with no bias voltage it conducts, and then I think in that case you have to go negative, and the other one's just the opposite of it. And they come in both N channel and P channel. Just like the JFETs, there's an N channel and a P channel. Then this chart has this MESFET, and I don't know what a MESFET is, so I'm not gonna talk about it. And it's definitely not on the exams. But I believe you have to recognize the symbol for FETs and transistors as a test question.
Yes.
You don't have to know how they work. So if we look at a basic JFET, and it has the difference between the N and the P is the direction of the arrow over on the gate.
And you remember that the arrow always points away from the positive. So it points to the negative. Easy way to remember.
Okay. And this shows kind of a example of how they're constructed, with the gate being in two pieces, and you apply the voltage there, which creates an electric field. So it actually, that's why they call it a gate, because it gates the electrons depending on how high that field is. You can actually pinch this off where there's no flow at all. And that becomes kind of a channel where you're going through this N material, in this case, from source to drain, or drain to source if you're doing conventional current. One thing to notice is they are symmetrical, so it really doesn't matter whether you use the source and drain the way they're supposed to, or you flip it around. It'll work the same. And this one down here is kind of showing the effect of the field, and how it, as that field increases, it kind of pinches off this flow. So it will allow fewer and fewer electrons to pass from one end to the other. This is just another thing showing, and we call that the depletion zone. And without any field on, I'm assuming this is an yes, an N channel. It's going to conduct current just like a diode. When we apply a negative field, okay, the depletion zone grows to the point where it cuts off conduction altogether. So that's how we use it as a switch or an amplifier. Like in the case of the transistor bipolar switch, we got cut off to saturation. You do the same kind of thing here. They don't call it cut off and saturation, but it's the same effect. Okay, so the other type is called a MOSFET, or metallic oxide semiconductor. Is it metallic oxide semiconductor, or I actually forgot what the S stands for. Anyway,
Transistor.
they take in a lot of cases, they say this is a polycrystalline material. It's some metallic material with its oxide as an insulator. So there's no connection. It's actually kind of like a capacitor, okay, between this and the body of it. And it does the same kind of thing. It creates an electric field, which will control the amount of current that can flow between the source and drain, or the two N-type materials in this case. And those are all the different representations. You see what changes is where the arrow is, and also whether this breaks in this or not, which I don't think I can explain the difference in that, but you don't need to know it anyway. At least not for a technician. This is just showing a simple operation of a MOSFET as a switch. So if we apply a positive voltage to the gate, we're going to get current flow between the drain and the source and light up this LED. In theory.
That's right.
This is just a selection of old and new transistors. As far as I know, they're still making these power transistors in these packages. I know they still make these. You don't see that many of this style except for, what is that? A 2219 is in that package, which is very common bipolar transistor. Here is this probably out of scale, a surface mount transistor. And these can become very, very small. Almost have to have magnifying glass to be able to see them or do anything with them.
And the older you are, stronger the magnifying glass must be.
Yeah.
Well, I need a magnifying glass for the big one there.
Yeah, I have a nice headset with interchangeable lenses and I gotta crank it up to the highest one. Oh, I just got for Christmas a USB microscope to do that. Got a nice little display. I haven't tried it yet. Okay, so what did we learn? Bipolar junction transistors use current to control current between the collector and emitter. Field effect transistors use a voltage on the gate as opposed to a current on the base. And it controls the current between the drain and source, equivalent to collector and emitter. And that the transistors are made, whether it's bipolar or field effect, by using N material and P material, or positive and negative dope material to create them. Probably the only difference I can think of with some of the diodes, like a pin diode, which won't be on the tech. I always thought it had to do with the way it was constructed, like a pin or something. Turns out it's a PIN, and it's P material, intrinsic material, and N material. So it has a piece of regular silicon in between those two junctions, and it gives it a different behavior. And then there's the Zener, which is a metal to N material. But I don't know enough, but I don't know of any transistors that use those weird configurations.
And so on, who knows?
Okay. Any questions on transistors or diodes?
Nope.
Okay.
Nope. Nope.
Today was a short one. I'll get out of here almost by noon. Takes 15 minutes to record or process the recording.
Okay.
Any questions about anything?